In our rapidly advancing and tech-focused society, it may seem strange to say, but for the past 50 or so years, we've been using the same, or fundamentally the same technology to run our computers. These semiconductor-based technologies have been utilize electricity to process information. And as these devices have gotten smaller and smaller, the amount of information we're able to process has increased. But this has come at a cost of energy. The energy is focused into smaller and smaller areas, and this has caused a larger amount of waste heat to be created. And dissipating this waste heat is needed in order to continue functioning. So this dissipation is a grand engineering problem, and it's something that our group has looked into. But there's another solution. So we can look into other technologies in order to reduce the amount of energy needed to do the same things. So this has brought about fields such as spintronics. So spintronics utilizes electron spin, or magnetism, to process information. By changing the direction of magnetization, we can store information, such as in computer hard drives, or we can process information, such as in the magnetic tunnel junction, that operates by having a low and high resistance state in order to determined by the direction of magnetization. So theoretically, these types of devices should operate with thousands of times less energy, but it's highly dependent on the materials chosen. So that's what I do for my research, is I look into these materials, try to extract the magnetic properties, and see if they're good candidates for spintronic devices. So in order to measure this magnetization, I need to have something that's extremely fast. So I use the fastest thing there is, light. I have an ultra-fast laser system that produces pulses of light that are 100 femtoseconds long. So a femtosecond is 1 quadrillionth of a second, so this is extremely fast. So this pulse of light excites the magnetization in the system, and then after some amount of time, I send another pulse of light on the order of picoseconds, or trillionths of a second, in order to measure the magnetization. Once I have the magnetization as a function of time, I can extract the magnetic properties and use these to determine whether these would be suitable candidates for these types of devices. So during my research, I've worked directly with other researchers and industry in order to measure state-of-the-art magnetic alloys, such as iron platinum for hard drives or cobalt iron boron for processing, such as in the MTJ. So my research should directly influence the design of spintronic devices in the future, and hopefully the computers of the future as well. Thank you.